Hi everyone, today we're going to talk about representations of three-dimensional figures. So we're still in our measurement unit, but instead of talking more about 2D figures, we're going to make the leap to 3 dimensions. So the first thing that we need to talk about is some terminology. A polyhedron is a three-dimensional figure whose surfaces are 4 or more polygons. Polyhedrons include prisms and pyramids, things like that. And so today we're going to discuss particular polyhedrons and the pieces that make them up. So in our first piece, we have a prism. So this is a prism. A prism is formed by two parallel, congruent polygonal faces. So here's my faces here. And they're parallel to each other, so they're never going to intercept, and they're congruent, so they're exactly the same size and shape. Those faces that are parallel and congruent to each other are called the bases, and they are connected by faces along the side that are rectangular. So these are the bases. And then these light gray figures that you see here, here, and here, those are all the rectangular faces. So today we're going to talk about a lot of adjectives for the shapes that you've been studying. So the adjective for something that is in the shape of a rectangle is rectangular. The adjective for things that are in a polygon shape is polygonal. So we're going to be talking about the adjectives for those shapes today. The next three-dimensional figure that we want to discuss is a cylinder. A cylinder is formed by two parallel, congruent bases in the shape of circles. So circular bases. These are the bases. And a curved surface that connects the bases. So it's not connected with faces like the prism is, it's connected with this smooth curved surface. So that's a distinction of a cylinder. Another three-dimensional figure we want to discuss is the pyramid. A pyramid is formed by a polygonal base So this figure down here is going to be some sort of polygon. That's its base. And triangular faces that meet at a common vertex. So these sides of the pyramid, those are all going to be triangular in shape. And they all meet at a common vertex. So this point right here, this is the vertex of the pyramid. And then the last three-dimensional figure we want to discuss on the front side of these notes is a cone. And the cone is kind of a hybrid. It's got some properties of a pyramid and some properties of a cylinder. So a cone is formed by a circular base. So just one, here's my base. And a curved surface that connects the base to a vertex. So that curved smooth surface is really closely related to that smooth surface that you see that's curved around a cylinder. So that's this right here. It's not made up of flat faces, and it converges up here to a vertex. So that's the vertex of the cone. So these are the official definitions and descriptions of prisms, cylinders, pyramids, and cones. In example 1, it says, name the prisms and pyramids by the shape of their bases. So first you need to decide if something is a prism or a pyramid, and then you need to decide what the shape of their base is. For example, in this top one, when we talk about a prism, these are the bases of the prism. These bases are triangular in shape, and so this would be a triangular prism. This pyramid right here has a polygonal base, and in particular, this polygon is a triangle. So this is a triangular pyramid. So you want to name the type of prism and the type of pyramid. So I'm going to name maybe 2, and then I'm going to let you name the rest and come back and check your answers. So maybe I'll name this one. So I notice that there is a base on top and a base on bottom. It doesn't converge to one vertex like these do down here. So this must be a prism. And now I need to look at the type of base. So it would be helpful for me to shade the base, or at least one of the bases, down here, and count the sides. So 1, 2, 3, 4, 5, 6. A polygon with 6 sides is a hexagon, so this is a hexagonal prism. Sticking with the idea of naming things with the adjective form of shapes that we've discussed in the past. The adjective for something that's hexagon shaped is hexagonal. Perhaps now I'll name this one. I notice that there's a base here, and not a base on the top, but a vertex that converges at a point. So this is not a prism, this is a pyramid. And I look at the shape of the base. The base has 1, 2, 3, 4 sides, and I notice that they all have right angles. I don't know anything about the side lengths of the base, so I don't know if this is a square or a rectangle, but I'm just going to go ahead and name it a rectangular pyramid, because I don't know if this is a square or not, but it's definitely a rectangle because it has 4 right angles. So this is a rectangular pyramid. So what I'd like for you to do is go ahead and pause your video. There are 8 total figures, and I've named 2 of them for you. So pause your video, try to name the remaining 6, and then check back to check your work. So you'll notice that the prisms and the pyramids kind of match up with each other. These 2 have bases that are triangular in nature, so this is a triangular prism and a triangular pyramid. This was a rectangular pyramid. We had done that before you tried to name the other ones. This is a rectangular prism, again, because the bases are quadrilaterals with 4 right angles, and I don't know anything about the side lengths of those bases, so I'm going to claim that it's only a rectangle. So a rectangular prism. These 2 have pentagons for the bases, so this would be a pentagonal prism and a pentagonal pyramid. And then these 2 have bases that are hexagons. This is a hexagonal prism and a hexagonal pyramid. So let's go ahead and move to the next page. So we're moving into a little bit more terminology. And instead of just naming figures, now we're talking about something that's just slightly different. We want to talk about a net. A net is a 2-dimensional figure that you can fold to form a 3-dimensional figure. So if we were in class like normal, we would take a net and we would cut it out and we would fold it along these little lines right here, these creases, and we would try and see what 3-dimensional figure it creates. So as an example, I've got a net out here, and it's unfortunate that we can't just fold paper in class today, but we can try to name the solid by kind of labeling these sides. So what I have here, I'm going to set this to the side. What I have here is just kind of a little shape. It does have no face over here, but that's okay. This is a rectangular prism. And so what I'd like to do is kind of use this to model the way that you would identify a net and what shape it is the net for. And so in a rectangular prism, you have a top, you have a left face and a right face, you have a bottom down here. So top, bottom, left, right. You also have a front and you have a back. So you've got all of those pieces, you've got 6 pieces. So what I'd like to do is go back to the notes and I'd like to label. So we're going to label something the bottom, and then we're going to try and build from there. So in this net, we're going to label this, it doesn't matter which one you use, but I'm going to label this B for bottom. So if I label this B for bottom, I want you to imagine this piece that's connected right here, it can only fold up at the crease. So if it folds up at the crease, and you've got a bottom and a piece over here that folds up, well, it's going to be the back. So maybe BO for bottom and BA for back. Well, if this folds up and is the back, then this piece right here is going to crease, and it's going to create this left side. So it's going to be the left. So now we have this crease down here with the next available blank face, and so it's going to fold up and it's going to create the front of your shape. So front. This piece will kind of fold to the side, so that will be the right. And then this one will flap over on and be the top. So this net right here is a rectangular prism. And we're able to tell that it's a rectangular prism because we were able to kind of fold and get all of the sides that we should get for a prism. So this is a rectangular prism. So now, example 2 says, choose the nets that will fold to make a cube. I want you to assume that all of the things here that look like squares are actually squares. Otherwise, we can't make a cube. So assume that these are all squares. Start out with something that you think might be the bottom. So maybe this will be the bottom. And start imagining it folding in on itself where there are creases. So if this is the bottom, this will fold up and be the back. This will fold up and be the front. This will fold to the side and be the left. This will fold up and be the right. And then this one will flap over and it will be the top. So it's got all the pieces. This will definitely make a cube. So now I'm going to do the next one. The next one I have, maybe we start here with the bottom. This will be the left, this will be the right, this will be the back. And then if this is the back and it folds up here, then this one's going to flop over and be the top, right? This here is connected to the left side. So we've got bottom, flap over, be the left, and this will also flap over and be the top. Which is no good because we've got two tops and we don't have any fronts. So this net does not fold to make a cube because it has an overlapping top and a missing front side. So what I'd like for you to do is pause your video and determine if the nets for C and D create cubes or if they don't. So pause your video and label the boxes to see if your nets create a cube. So hopefully you were able to label the bottom, the left, right, back, front, and the top. You were able to conclude that the net for C and the net for D both create cubes. So let's move on to the next section. We've got more terminology. The definition of a cross section is the face, so like the surface, the face you get when a plane, remember a plane, not an airplane, but a geometric plane, like a paper or something like that, that extends forever in all directions and is flat. A cross-section is the face you get when a plane slices through a 3D figure. Below is a sample slice through a cube. So imagine a plane kind of slicing off the corner of this cube. And the part that's exposed is the cross-section. It's that face. And this face happens to be a triangle. So this shows one of the cross-sections that you can get if a plane slices the cube in this way. The shape formed by the slice is called that cross-section. And it's important to note that the cross-section cannot contain any piece of the original face. So we're not taking the cross-section of this square over here. We're taking the cross-section of interior pieces of the figure. So it all comes from the inside of the solid. In this picture, only the gray piece is the cross-section. So it's what's left exposed from the inside of the 3D figure. So you can kind of imagine this was the cube, and then this little pyramid part got sliced off, and we have that triangle as the cross section. So the bottom says, draw and describe each cross section. So it doesn't really have what cross sections you're supposed to draw, but I'd like to describe some of them. So let's draw a cross section here if a plane slices vertically. So a vertical plane. So I'm going to go ahead and draw in a vertical plane. Perhaps I have this piece, and this piece, and this piece, and then it comes down back like this. And all of this part is taken out. So the part that's been taken out is this over here. Okay, so that chunk is gone, and the exposed part that remains is parallel on top and bottom, and then we've got parallel lines here, and so what it creates is a rectangle. So that's what happens when you have a vertical plane creating a cross section of that triangular prism. Now let's talk about if you have a horizontal plane. So maybe we have a plane like this. So we have a plane like that, and it's kind of slicing in here, and it's coming out and slicing that way. So maybe we're taking this top part off. And if we're taking that top part off, the part that is exposed is this right here. So the cross section is a triangle. Perhaps now let's do another vertical plane on this. Almost looks like a cube, but I'm not for sure if it's a cube. So we'll talk about a vertical plane slicing through and creating a cross section on this rectangular prism. So let's go ahead and draw our plane. Maybe here. Like that. And it's slicing through here and here. So this piece it's slicing off, and it looks very closely related to this one over here because what's left is a rectangle. So if you want, you can kind of shade in that cross section so that you can better see what it is that's exposed whenever you slice through those 3D shapes with a plane. So the last page in our notes today continues the discussion about cross-sections, but we talk about a pretty important cross-section, and it's called a conic section. Conic meaning the adjective for something that is cone-like in shape. So a conic section conic section is the intersection of a plane and a cone, or a double cone, so like one that's on top of each other. You have an example of a double cone here. So this is a double cone. Many conic sections can be modeled by equations in x and y and x squared and y squared. So we'd like to graph each equation and then match it to the correct cross section that's below. So we've got these cross sections that are created. And if it helps, you can go in and you can color in the cross section. Okay, so coloring in these cross sections might assist you in figuring out what these shapes are. Of course, you don't have to color in all of them. You don't have to color in any of them if you don't want to, but I thought it might be useful to color in those cross sections. So now I'm going to go to my graphs. Each one has an empty graph and an equation, so I'm going to graph my equations, and then I'm going to try and match them to my respective conic section. So in the first graph, this is the equation y equals x. This is the linear parent function. It kind of models. It models all of my lines that can be written in any form, particularly y equals mx plus b, slope-intercept form. Many students are familiar with that. My y-intercept here is 0. My slope here is 1 over 1. So when I graph this, I start at a y-intercept of 0. I rise 1, I run 1, and I continue until I'm off of my graph. So I'm going to use a straight edge to create that straight line. And here my conic section is a line. So when I go look at my answer choices, the only one that looks like it's a linear conic section, this doesn't look linear, not linear, not linear, not linear, but this does. So just slicing off the very, very edge, that's graph E, or cone E. Okay, let's move on to the next one. We've got x squared plus y squared equals 9. This looks an awful lot like the equation of a circle. Remember, kind of the standard form for the equation of the circle is x minus h squared plus y minus k squared equals r squared, where h and k are the circle's center and r is the circle's radius. Well, h and k don't seem to appear here, so the circle's center must be at 0, 0. And the radius squared is 9. So if you square root the radius squared, the radius is plus or minus 3. Now we can't have a negative distance for radius, so we're just going to say 3. So I'm going to count 3 in all cardinal directions. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So here's my circle. Drawing it as best as I can. And I need to go find the conic section that matches a circle. So in my choices, this is gone. I already used it. This has a straight line here. That's not going to create a circle. Straight lines here and here with 2 sections, not going to be creating a circle. My choices are this one and this one. But if you think about these, this conic section is a little bit longer because it's diagonal than it is wide. So that's not going to be a perfect circle. This will be my perfect circle. So B is the conic section modeled by a circle. Next graph, y equals x squared. This is the classic parent function for a quadratic function. It has a vertex at 0, 0. And the quadratic pattern is every time you go over 1, you go up an odd number. So over 1 up 1, over 1 up 3, over 1 up 5. Do the same thing on the left side. Over 1 up 1, over 1 up 3, over 1 up 5. So here's my parabola. So I need to go find the conic section that creates like a parabola shape. So I've used these two. This is not a parabola. This almost looks like 2 parabolas. And here is one single parabola. So C is the conic section that creates the outline of a parabola. Okay. My next one looks an awful lot like a circle, but it's not a circle. And so it's going to match the conic section that's almost circular, but not quite circular. This creates an ellipse, and we haven't talked about how to graph them, but it is important to know that ellipse and circles are very closely related in structure and by equation. So this is an ellipse. This is going to match this conic section, so D. And finally, we have one last problem. It must match A. It's not something that looks like a familiar equation to us, so it might be a good idea to pick some x values and create a table, because we're not really sure what this looks like. So perhaps I'll pick -2, -1, 0, 1, and 2, kind of the typical x values to choose when you don't know what's happening. So if I substitute -2 for x, -2 squared is 4. If I add 4 to both sides, I get a 5. And y squared equals 5 gives me a y value of plus or minus the square root of 5. If x is -1, then I'm going to put -1 here. -1 squared is 1. If I add 1 to both sides, I get y squared equals 2. And that gives me a y value of plus or minus 2. Or sorry, plus or minus square root of 2. If I put 0 here, the whole term disappears. Y squared equals 1. And so y equals plus or minus 1. And then whenever I substitute the positives for 1 and 2 here, when I square them, I'm going to end up with the same answers that I had for y. So this will give me plus or minus square root of 2, and this will give me plus or minus square root of 5. So when I graph these, when x is -2, y is a positive square root of 5 and a negative square root of 5, and that's about, 2.2. And so I'm going to go up 2.2, and I'm going to go down 2.2. When x is -1, the y value is plus or minus square root of 2, which is about 1.4. So I'm going to go up 1.4. I'm going to go down 1.4. When x is 0, y is 1 and -1. So here and here. And then I've got repeating values, y values for these positive x's. So this graph, this point and this point, this point and this point. So it looks very much like the conic section that is left over in this one. So we've had an introduction to the basic three-dimensional shapes, nets, cross sections, and more specifically, conic sections.